All right, folks, here we go. Day 2 of notes for us, okay? So what we've got here today is rotational kinematics. Now, don't fret too much. Rotational kinematics isn't something majorly difficult. It just is going to take a little bit of work remembering what is what and what represents what. So what you're kind of seeing here in the bottom right corner is a fishing reel and the ability to be able to translate kind of that rotational bit to the actual line going out, so to speak. And then on the left, you've got the swing ride at Mall of America. Obviously, the faster you start to go, the wider we start to end up getting. If we were to look at this as a linear velocity, if all of a sudden something catastrophic were to happen where this top little bracket up here were to get cut, well, then that young lady here is going to fly off in a linear direction, so to speak. Hopefully it doesn't happen, right? All right, rotational kinematics for us now, okay? Like it says on here, this is very similar to linear kinematics. And I know that we went through a bunch of those, used them in a bunch of different frames and ways and shapes and forms and everything like that. And we'll try to be thorough in the beginning here to get you to understand kind of how to do these different setups and different problems so that you can feel comfortable with them as well. All right. The only difference now for us between those linear and these ones is everything's on a spin, on a rotation, stuff like that. Okay. Our variables, we're going to have theta here, right? Theta is going to be our displacement or distance measured in radians. So if you have revolutions or rotations, you have to multiply that by 2 pi, remember? So if you have 1 rotation, you have 2 pi radians. If you have 10 rotations, you have 20 pi radians, all right? Omega, remember, that's our angular velocity measured in radians per second. Omega final, or omega f, is our final angular velocity here. Omega I, that's our initial angular velocity. Alpha, that's our acceleration in radians per second squared. Now, to be fair, I'm not going to mess with you on this one. On the velocity one, I may put in there revolutions per minute or something like that. Remember, to convert revolutions per minute to radians per second, multiply by 2 pi, divide by 60, okay? Time is in seconds. That's a pretty standard one for us, all right? So here's our formulas. Now, if you want to, just take a glance at these. I've got a better slide on the next one that shows kind of everything that's going on with what we have, all right? But it at least gives you an initial gist of what's at stake here, so to speak. Okay, so here's a nice little slide for us. Yesterday we talked about kind of these top 2. We also talked about the conversions on the bottom. So the bottom 3 are our new kinematics. Now, to be 100% transparent, the second and the third equation really are the same thing for us. All right, when you look at those 2, this one, the third one is just expanded out. All right, so we got final velocity equals initial velocity plus acceleration times time. It's like over here, all angular. All right, angular final velocity squared equals angular initial velocity squared plus 2 times the acceleration times the displacement, the number of radians it's gone around in a circle. All right, displacement here again, or distance here, so the number of radians it takes to go in a circle, equals our initial angular velocity times time plus 1/2 the acceleration, angular acceleration, times time squared, right? And again, we've seen those over there. The nice thing about these bottom conversions are it allows us to translate that into distance. So we can talk about the distance it's traveled. We can talk about the velocity it would be going if it were shot off from that in a straight line, so to speak. And we can talk about how much is it accelerating if it were to be slowing down off or after that point, so to speak. Okay? All right, so here we go. Practice for us, okay? A carpenter cuts a piece of wood with a high-powered circular saw. The saw blade accelerates from rest with an angular acceleration, from rest, nice number there, right? An angular acceleration of 14 radians per second to a maximum speed of 15,000 RPMs. RPMs, messy, all right? What is the maximum speed of the saw in radians per second? How long does it take the saw to reach its maximum speed? How many complete rotations does the saw make? And if the safety mechanism brings the saw blade to rest in 0.3 seconds, what is the angular acceleration does that require? Okay, so number one now says, what is the maximum speed of the saw in radians per second? Now, something big that I'm going to try to get you to do a little bit more of are these data tables here. Just because the tricky bit with this is understanding what we have, especially in this chapter with such weird measurements of radians per second or stuff like that, and being able to say, all right, this is a label that I have, this is the unit that it represents, okay? So angular initial velocity is 0, right? Accelerates from rest. Our final angular velocity is 15,000 RPMs. That one doesn't work, as you see in part 1. And then our angular acceleration is 14 radians per second squared. All right. So for us, we want the maximum speed in radians per second. Right? So we take our 15,000 RPMs, multiply them by 2 pi. That gets the revolutions into radians. Divided by 60, that gets the minutes into seconds. And we get 1,570.8 radians per second. All right. Now, for a little bit longer, we'll give you points for that step, but probably after next week, we'll stop asking that question because we'll assume that you can adjust radians per second, or I'm sorry, revolutions per minute into radians per second. All right. That becomes a huge deal for us, and your ability to do so becomes imperative, right? That's like saying, I've got kilometers, I can convert it to meters. That's like I got grams and I can convert it into kilograms. It's just one of those steps that we have to be able to do. All right. So, excuse me. How long does it take the saw to reach its maximum speed? So now what we've got is we've got our initial angular velocity. Notice the change here. It's in radians per second, so it's a better number for us, right? And then we've got our acceleration here. So what we need is how long? That's a time. Okay. This first equation here is a no-go. That's because this is just an average angular acceleration for us. So we can't use that one. Next one, we could use that one, right? Because we got a change in it. Third one for sure we could use. All right. I gotta move sorry, I had my picture there. This one here doesn't have time. This one here, we don't know how far it's gone, right? So between the second and the third one, those are the ones we're going to use. Now I'm going to use the broken out third one or the split up third one just because it looks a little bit cleaner. All right. So final is 1570.8. Initial is 0. My acceleration is 14 radians per second squared. And then there's my time. Rearrange all of this. We get 1570.8 divided by 14. That's going to take roughly 112.2 seconds for us to get up to speed, right? Get up to that maximum speed. So a little under 2 minutes for this to run that way. All right. Next one. Oh, I didn't fix my animations on this one. Sorry. All right. Third one says, how many complete rotations does this saw make? All right. So now I put in my time here. All right. Complete rotations is going to be our theta. So again, we can't use that top one. The top one is only if we have like an instantaneous one and we want to find the average velocity. That one becomes kind of a slippery slope for us. All right. Can't use the second one, doesn't have a distance, doesn't have a delta theta. Third one doesn't work. Oh, okay. So we could use the fourth one or we could use the fifth one. Now, just so that you're aware, I use the fourth one, but I also tried out the fifth one and it does work. All right. So we put in our final velocity here, right? Final angular velocity there at 1570. Initial is 0, 2 times our acceleration. All right. 1570.8 squared is 2,500,000-ish, right? 2 times 14 is 28. Divide that. So what we end up seeing here is we get 88,121 radians. That's how many times it went around. Now, because it's asking for complete rotations, I divided this by 2 pi. Now, be aware, this number was actually 13,000. Oh, wait. Hold on. Messed it up. Oh, I forgot some numbers in there. I forgot a 4 in there. Let me fix that. So this should actually be 80. Let's make this right. 88,121 divided by 2 pi. That is actually 14,024. Now, it is, just so you know, 14,024.8927. All right. It didn't make that 25th rotation. So we basically have to round down on this one, take whatever number is in front of the decimal and use it that way for our complete number of rotations. We can't have, 0.9 rotations. Okay, sorry about that. I forgot parentheses. Holy cow, that's bad. Whew. All right, part 4. The safety mechanism will bring the blade to a stop in 0.3 seconds. I should have switched this thing out here, so I'm going to write that in there. This actually should be now 0.3 seconds. Okay. So we want to know what is the angular acceleration of this, right? So anything that has angular acceleration for us is going to work, right? So second one, third one, we don't know how many revolutions it takes, so we can't do that. We don't know, again, how many revolutions it takes, so we can't use that. So really, it's our second or third one, okay? The expanded second one works really, really well. So we get our final velocity now. Angular velocity is going to be 0. Our initial is going to be 1570. And then we got alpha times our theta there, okay? So move over the negative 1570, divided by 0.3, we find that this thing should end up rotating at about negative 5,236 radians per second squared. All right. So hopefully that makes sense. Sorry for the mess ups and mistakes on that. I thought I had it better than that, but I guess I didn't. Okay. Tangential speed. Crazy part about tangential speed is we've actually begun to discuss this. We just didn't call it tangential speed. All right. So your tangential speed would be this right here, is that red arrow. Right. So when we talked about, on the gravitron, all of a sudden a trapdoor opening on a gravitron and you flying out, well, that's what we mean. Or the little girl on the front, if all of a sudden the bolts on the top sheared off and she flew out, that would be her tangential velocity or her tangential speed. Okay. So the red arrow really shows that for us. The couple ways that we can make this change is spin the merry-go-round faster, right? And then make the merry-go-round bigger. Now, if we spin it faster, that increases our omega, right? If we make the merry-go-round bigger, that increases our radius. So those two become kind of integral parts for us in our problems there, right? Make sure at some point in time over the next 3 or 4 days, you check out the practices. Those will go online. Also make sure that you work through the first 2 sections of homework as well, okay? Otherwise, that's that for the day. Talk to you.